Here we start off with Go Write Your Own Database by Tahir and Hari.
So good afternoon, everyone. I am Tahir, and Hari and I are here to talk to you about writing custom databases. Right? I mean, conventional wisdom says that writing databases is a really tough job. Most of you should not even attempt to do that. But given the fools that we are, we actually tried it for a use case in logistics, and it actually worked out well for us. So we're just going to go through why we chose to write our own database and how it helped us. So to begin with, whenever you need to write an application that requires storing data somewhere, you need to choose what database you want to use for it. And typically the choices fall in two categories. You can either go with a relational DB, and we all know that it comes with a sophisticated query language, and you have nice data modeling primitives over there, and you can control transactions in a fine-grained manner. But on the other hand, the problems with RDBMSs traditionally have been that it's very difficult to change schema as your application evolves. Generally, RDBMSs also have average latencies on the slightly higher side. And if you want to split your data into shards and you want to do, complex transactions and you want to normalize your data neatly, you end up having a lot of pain. That pain somehow is not showing up. All right, so yeah, we were talking about the choices that we have for databases, right? On the one hand, we have relational databases that are good for writing, complex queries and data modeling, sophisticated data modeling, and fine-grained transactions. But on the other hand, they are kind of slow and difficult to manage, right? And so there is a new, well, now they're old. There's a new set of databases which are called NoSQL databases, mainly because they don't require you to define a schema upfront. So they are schema-less. And usually they're also low latency, high QPS kind of systems because they use in-memory query processing a lot. And they allow you to easily scale up, as in you can add a beefier machine, and they allow you to scale out as well. You can throw more hardware at them and they'll somewhat get the job done. But they run into problems where RDBMSs shine. So you don't get a lot of sophisticated transaction modes. So typically what you would do is maybe try remote locking or do a get, modify, update kind of changes. The query language, well, is basically CRUD operations plus a bit more. And if you have like nicely structured data that you want to put into it, you run into problems with querying or processing that data inside the database. So that's the world of general purpose databases, and we ended up with having a problem where our domain did not fit well into either of those models, and that's basically about tracking logistics capacity, right? So when you go to Flipkart app, let's say you choose to buy a product, what we do is we have to look at our map of India. Well, we don't have a map, but yeah, we still need to find all the sources where we can ship that product from. We look at where you are placed, and then we try to find connections between the sources to your location. And so some of the sources are not connected, so we need to discard them. Some of the connections may be out of capacity. And when I mean out of capacity, it means that even though there is somebody who is ready to take your product to your destination, they may have run out of the ability to ship. Like they can only do so many orders every day. So we drop those connections which do not have capacity, and then whatever is left out of that, we select the the fastest or most preferred kind of connection, and then we make a promise to you saying you will get your item tomorrow or something like that. So here's what the problem for finding a vendor is, represented in something like SQL. We tried hard to put it in English, and it was turning out to be really bad. So what we need to do is find a vendor who is actually preferred. If you look at the order by, there is a vendor priority, and that priority changes based on the product. So we need to find a preferred vendor who is available at the earliest possible time to deliver the product. And we have some kind of what we call a calendar, which is a database of all the metadata that we need, and that data is namely what destination we want to ship to, what is the number of units that we need to ship, is there any specific capability, like should the vendor be able to do next day delivery, or should they be able to carry dangerous goods and so on. And then for each vendor, we can't just do a sort by time and get it, because the date at which the shipment will reach the destination differs for each vendor based on their own internal logistics. So it's a fairly complex thing, and it still doesn't cover the per query vendor prioritization part of it. So that is the vendor search, and then consuming their capacity. Now people, as they place orders, we need to block the vendor's capacity and we need to consume them. So we have primitives around soft reservation, hard reservation, etc. Or we want to do a search and reserve kind of an operation, and then we need to be able to undo all these things. And in some cases, we also want to allow overbooking in a controlled fashion, saying that, okay, we'll take the order even if the system tells us that there is no more capacity, and then we'll try to adjust it offline, right? And then maintaining all of this metadata in the transactional system has its own constraints. We need to be able to add delta capacity or absolute capacity to the vendors, adjust reservations in case there has been a capacity reservation reduction, and typically what we have is basically a look ahead, like from today on for the next n number of days, we have all of that data. And since today's data is useless, so we need to be able to purge the data on an ongoing basis. So that's broadly the problem set, right? And just to clarify it a little bit, in terms of data modeling, this is what it looks like. So we have a two-dimensional structure, right? And every row is basically keyed on a time slot. The time slot may be, say, days for regular shipments, or they may be, actual hour slots. Like for TVs and large appliances, we have slots, right? Multiple slots per day. So that's the time slot, and then at that slot, we have a bunch of vendors who are available to ship it. And then this calendar goes on, like the first slot, then the next slot, and so on. And these time slots need not be at fixed intervals. The delta can vary, right? Number of vendors can vary. Like in the second row you see here, there are more vendors than in the first row. In the third row, some vendors have disappeared, and in the last row, some vendors have come on board. So all of this is very dynamic, and this is like real data. These are the constraints that we work with. And for each vendor, the data that we record we basically record three numbers. One is their maximum configured capacity, which helps us in keeping track of changes to delta changes to capacities, etc. One is the available capacity. So this is what we just need to look at, one number per vendor to check whether that vendor can ship or not ship. And then there is the number of soft reservations, like how much capacity have we blocked for taking orders later down the stream in case the checkouts proceed, right? So that's our data model roughly. And so given this problem domain and given this kind of data model that we wanted to have ideally, we tried to solve it with some of the database choices that we had available. And I'm going to present two of them just for example. We actually evaluated several databases. So on the RDBMS side, we thought about MySQL, and then, first off, the immediate problem with MySQL is that the average latencies are high, right? And our QPS requirements on that system were also pretty high to handle all the scale. So we couldn't have done with, like, say, even with one giant machine. So sharding had to come into picture, etc. And so it was complex. And then let's say we try to model that two-dimensional matrix as a single table where you have the time slot as a primary key, and then we have each vendor as a column. So the problem there is, MySQL doesn't allow varying number of columns, and there is a maximum limit to the number of columns that you can have. And neither of those were good for us. And then we thought, okay, maybe we can have one vendor per row kind of a system, and then that is what would have led to the query that you saw earlier in the problem statement. So the SQL was complex. It is somewhat difficult to verify whether it is doing the right thing. It's also difficult to optimize, as in what kind of indexes you have to create and all that stuff. And then, um, it does not also evolve very easily. Like if you want to add some edge cases here and there, adding those edge cases in SQL becomes really difficult. So MySQL went out of the picture, and then on the NoSQL side, we considered multiple options. I'll just present Redis here because that is the one that came closest to being, greenlit. The immediate problem with MySQL was that we have a lot of numbers, like all of these capacity numbers. We have to track all of them, and our projection was that we'll need about 3 million integers stored in Redis, and at peak throughput requirements, we would need to be doing about 5 million commands per second. Now, Redis can do a lot of commands per second, but 5 million is still too much for a single node. So we would have had to split our data. We didn't want to split our data. And if you wanted to have these capacities in Redis, we had two choices. One is that, we either get all the capacities scanned and then ship them off to the application where we do that logic of going through the days, or we let it be done inside Redis with a Lua script and all. So in the first case, the I/O overhead was unacceptable. Like it would have led to high latencies anyway. In the second case, the script itself was slow. We prototyped it, it didn't work out. And so Redis was out, and similarly MongoDB and a few other things. So we said, what about writing our own database for it? And so immediately the benefits are that we could basically just design it to solve our very specific problem. So the schema is under our control. Queries, we can basically program the queries right into the database. We can define the transaction model as we need it, which is basically to have maximum concurrency possible for each separate counter, because every query looks at, say, 10 to 15 or maybe even 50 to 100 counters. And if we block on each query, then our latency would go up because everybody would be waiting in a queue to scan all of those counters, right? So, and then the efficiency, the compute efficiency in terms of scanning all of that data per query, and the I/O efficiency in terms of not having to, like in case of in-app logic, ship all of that data back and forth between the application and the database, right? But there were big, problems to consider. Like, first of all, performance. How do we even know that we can write something that would be faster than Redis? How do we know, how do we decide on what to use on the network and client library side? What do we do about durability and replication? Those are difficult problems. And how do we guarantee high availability? Because this is a system that is, it's used to answer queries for people who are just looking at the website, right? You go to a product page, you see a promised date, and that needs to be high availability. We can't afford to not show you a date. So how do we handle that? And so we'll take a look at how we addressed all of these concerns. But before that, I'll just talk about what the AKM server, AKM is the system that does all of this, what we wrote. So what it looks like. So at the core, what we did was started out with writing, basically a native application. We designed our core data structure. We applied our business logic to it, those queries, the search queries, the update queries, etc. And we provided native APIs. So this was written in Go, mainly because at this time, I think if you want to do high performance compute and you have time to market constraints, then Go is the best choice, period. So we wrote this core and we did some validation around it. And as soon as we were satisfied, we added the server component. And the server component is basically what allows taking this data or this application from your local box to network clients, right? So we wrote the RPC adapters and we designed the network protocol. And then finally, we did something about the replication. Now this Datastore is, in the context of this presentation, it's a bit misleading, but that's what we ended up calling our, snapshotting and replication setup. So this Datastore component is responsible for snapshotting all the data and providing replication and restoration features. And then there were some horizontal components like logging and metrics and profiler and installer, which apply to all of these components together. yeah, we actually have a profiler that we can invoke on demand in production, get an idea of how the server is performing in case we notice any problems. And for those of you who are somewhat familiar with Go, this is what our code layout looked like. So we went with a project, a Go project management system. It's a fancy word for what it does, called GB. So you can go to getgb.io and get that thing. What it allows you to do is, have like a standalone directory in your dev box, and you can lay out your code in there and um, have it independent of your global Go paths, etc. So it provides a project context. By the way, how many of you here have worked with Go? Oh, not many. Okay, I'll try to skip this part then. So yeah, basically we have three sub packages there. AChem is the core, AChem D is the network server, and under the command directory we have the main, which basically starts the application, and all of our dependencies are pulled into a vendor subdirectory. So coming to challenges, right? One of the first challenges was performance. Like, how do we, and this is critical, right? I mean, we rejected things like Redis and all, saying that they will not perform well for us. How do we even know that we can write something which will be more high performance? And so from a first principle point of view, the most important thing here was to make sure that the our application is like highly dependent on the data structure, the data model, right? And so we wanted to have the most high performance data model that we could design within experience and time constraints. So so Go allows a tighter control over your memory layout than reference based languages like Java or Python or Ruby might allow. So we used Go structs, which lay out all the fields, in one contiguous block of memory. We also used slices a lot. They're like, Java arrays rather than lists or something like that, in that they don't have references to each element. They basically just lay them out in one strip of memory. And wherever we need these aggregates, we just pre-allocate all of the memory, place the items into it, and try to minimize mutations to it as far as possible, right? So that was about the memory layout. So the memory layout has to be compact so that it can utilize the benefit of CPU caches. Like I think Alex talked about how iPhone 6s kills everything just because it has on CPU caches, right? And there's another interesting, short interesting video by Strausstrup about insertion in a C++ vector, which is basically just a fancy array, versus a linked list. Now, if you go back to your college days, you would have learned that the O and complexity of inserting in the middle of a linked list is less than that of doing it in an array, because you have to do a lot of shifting and all. But in real world, because of the CPU cache, the vector-based shifting sequential insert actually outperforms linked list by orders of magnitude. So that's what we tried to exploit here. The next problem we need to tackle was the garbage collection, all right? Because Go is a garbage collected language. We could not afford to have GC pauses, spoiling our party. So the key principle there is to minimize the number of pointers that you have in the system. Like again, pointers might be alien to Java developers, but any place where you address a memory location by reference rather than directly hooking into it. So in Go context, that mainly means avoiding strings, and that's good even in Java. So we have hash maps where we did not use string keys, we used integer keys to make sure that we don't have strings in there. Otherwise, we would have had a lot of pointer tracking overhead. And we use buffers, which is again a good practice even in Java. When you need to build strings or textual data, you should try to use buffers which are pre-allocated strips of memory. You can just insert your data right into them. And Go has a buff.io package which is very easy to use, and it's ubiquitous, and it's available everywhere. And it seems like some of the content is being cut off because there is another point about using a sync pool object pool that Go provides. So the Go standard library provides an object pool that automatically resizes. It's concurrent to access. You can just throw your reusable objects into it and take them out of it. And all it needs to know is how to create a new object if needed. And it'll automatically take care of reducing the size of the pool if the memory pressure is high, or if it's not high, then it'll keep things around. So yeah, we utilized all the performance goodness of Go in making sure that we got good performance characteristics right from the beginning. And the other advantage of doing this as a custom database is that all the data was stored in native binary representation. So we didn't have any per query overheads of serialization, deserialization. Like if you use some of the other databases, like let's say maybe MongoDB or even Redis, if you try to use it as a document, they will serialize your data and then on every query deserialize it and do some operation and put it back when you do a write. And here we didn't have any of those overheads. And since this is mostly numeric data, it worked very well. We provided for concurrent access to each capacity object. So all of these different vendor capacities, right, they are individually accessible. They have their own mutexes. So while there is a query that is scanning a set of capacities, we can have another query scanning the same set of capacities, and as long as they don't tread on each other, it's all fine. And for writes, we have multi-level locking. Like we don't, unlike Mongo 2, we don't like lock the entire database for making updates. So only if we need to add a new calendar, we lock it for a few hundred nanoseconds to insert in the map. If we need to add new time slots, we lock the calendar alone. So it's only the calendar that is being modified. And again, there we've tried to minimize the amount of time for which we hold the locks. And capacities are all completely concurrent. And we wrote the query logic also in Go. And so the advantage is that, first of all, we could customize the query. So we don't have any auxiliary data IO being sent, like in the SQL queries, you have to send your conditional data, and you have to also send your query syntax, etc. down the wire. No such overheads here. And we didn't even need query optimization, because when we benchmarked this, we were getting like millions of transactions per second out of that native application, right? So we nailed performance. And what helped us big time in nailing the performance in the core is basically this loop. The code, you write code, then you test, you do the unit test, and many times you just stop there, right? The benchmarking is taken care of in production. But in ACAM's case, we did benchmarking right after every commit. And not just that, even profiling. And then that went in a loop. So at any point of time, any commit in Go, in ACAM would have gone through multiple benchmarking iterations. And again, there is some stuff missing there. We have about 10 benchmarks on an average, and we did about 50 benchmark runs per commit into ACAM. So we always knew where the performance bottlenecks are, where we need to address, where we are okay, etc. And that might seem like a big task, right? I mean, it's a lot of discipline. Having to write code and then unit test itself is a bit difficult, and then you also have to benchmark and profile and all. But Go's toolkit, the standard toolkit, like no dependency, you don't have to go and say, oh, I want a unit testing framework, I want a benchmarking framework, is the Go standard toolkit, which allows you to do this and do this very fast. Like, would you believe it that we can do it like in 10 minutes? We can go from unit test to benchmarks and analysis. Well, I can actually show you how it is done in less than 2 minutes. So here's a video. Let's say you've committed some code and you invoke the unit testing framework, and it compiles your binary, it runs all the unit tests, let's say they pass. So you start running the benchmark. So go test minus bench, and you give it a substring which will run the benchmarks for only the benchmarks that match that substring. And while the benchmarks are being run, you can also dump a CPU profile or heap profile, or multiple profiles are possible. So in this case, we are dumping a CPU profile, right? And so we're running the benchmarks, seeing how many iterations per second, what is the average throughput, the inverse of average throughput in nanoseconds per operation, and so on. And then at the end of it, what we get is basically that the CPU.prof is the profiling output, and then we can use the standard Go profiler to analyze that profiling data, right? So we're just going to load it up and see what are the top CPU hoggers, and we see that it's some syscall that is taking half of our CPU, right? And so we want to go deep into it and see why is that. And it turns out most of it is network I/O, and even in network I/O, the writes are more expensive. But if this text UI is not good for you, then you can even draw a nice chart and have it open in your web browser. You can pan it and zoom it and do all those kind of things. And this is less than 1.5 minutes, what you've seen here. So in 1.5 minutes, you make a change, a code change, you get data feedback about what impact it has had on performance and whether you fixed any performance issues that you were set out to fix, right? So core performance taken care of. We got like millions of transactions per second out of the core. The next issue was to tackle the network and clients, and this is where things get a little less exciting. So we started out with prototyping HTTP, JSON over HTTP, and that was just a proof of concept. We didn't go far with that. What we did instead was do JSON over WebSockets, right? And the advantage of WebSockets is that they allow you to actually utilize your underlying TCP connection to the fullest. It's like full async. You can keep dispatching your messages down one end. You can keep receiving responses down the other end. There is no stopping. Unlike HTTP, where if you send a request, until the response comes back, you cannot use that connection, right? And then you end up opening a huge flood of connections in a high throughput system. No such issues here. Full duplex async messaging. On the clients that we had, though, were not ready to work with WebSocket. So we also developed an HTTP 1.1 to WebSocket bridge proxy, which I think was about 100 lines of Go code, not very complex. And then we removed that in version 2 when we had more time, right? So the clients were also speaking directly WebSockets. And what we found was that we had a bottleneck with our JSON CDS. So we changed the JSON format a little bit and also hand wrote the JSON serializer, and that gave us like a 1.5x performance boost. And then I was talking about those buffers and buffer pools, right? We discovered that as we improved the network performance, the GC started becoming a bottleneck, and so we used buffers and buffer pools for managing the allocations. And we added request batching support. Like we saw in the profile that the call to network is taking up a lot of CPU. So one way to minimize that is to do fewer calls for more queries. So we added request batching, which gives us up to 10x higher throughput. And this is graphically what it looks like, our performance benchmarks. The last one, V2 tuned, right? I mean, we were benchmarking our application and we had a target for some insanely high number, and I just got a call saying AKIM is not performing, and we were like, it was doing some 1/10 of what we needed it to do. And so we just went there, examined what is happening. It turned out we had compiled with Go 1.5, so one change we did was to compile it with Go 1.7, which has an awesome new compiler backend. It uses something called static single assignment analysis. And what it does is allows you to get rid of a lot of temporary variable creation, etc. And so that gave us a performance boost. The other thing we did was, well, we didn't need a lot of RAM. Go runtime is anyway like 5x or 10x more frugal on RAM than say a Java-based runtime. And we had enough RAM available on our boxes. So we said, okay, can we ease some GC pressure? So there is just one GC tuning parameter in Go. It's called Go GC, and it's a percentage, as in the overhead of reclaimable memory over what is being used, and the default is 100. So if the memory becomes double of what you need, the GC will kick in, and we just set that value to a higher number. We chose 800. That's it. Ran our benchmarks. Wow, we met our targets. It was literally 5 minutes of effort. Okay, so now I'll take a break and invite Hari to talk about our durability and replication and other challenges. Hari, take the stage.
Hello. Yeah. Okay. Thanks, Tahir. Okay, I'll be talking about how we have achieved replication and high availability for AChem. As you would have already figured out that AChem stores the entire data in memory, and if the process goes down, the data is lost, which is unacceptable. So we have to get this data replicated across other machines so that if one process goes down, the data is available in other machines and they can take over and start serving the request, right? And as you know, replication is a hard problem to solve, and probably right after lunch, I think it's really hard problem to solve, right? So, but thanks, yeah, as hard as it is already a solved problem. There are many solutions out there who has already done replication very well, handling all the corner cases and edge cases. So we didn't want to reinvent ourselves. That obvious reasons, like one, we want to cut down on the development costs and make it available to production as fast as possible, because we already solved our core problem. And yes, there are solutions available, then why not? So we try to piggyback on the existing solutions to handle replication. So what we have done is we store the entire data into a co-hosted Redis. Okay, so why Redis, right? Everyone knows Redis, right? Anybody who, okay, knows, doesn't know, knows? Okay. Okay, Redis is a key value store, right? And Redis also provides replication, and we have already used Redis in many production setups, and we know that it works very well on what it's supposed to do. And so what we did is we transferred the data asynchronously into Redis. So again, there are choices. You would have remembered the layout, right? You have a calendar with cells having those numbers, the counted numbers, right? So we have choices again, like, okay, what data should I transfer into Redis? Should I transfer like every cells as and when they change online? Or that is not acceptable because you know that adds to my write path latency. Oh, should I sync every cell asynchronously? Oh, then I need to track on the failures and okay, how many keys, like what if the Redis is not available for some time? What do I do? And how do I correct it later on, right? So that's why we have made a simple choice. We said, okay, let me snapshot the data, right? And which is what even Redis internally does for snapshotting. So AChem snapshots the entire data asynchronously and stores it to Redis periodically. And you use Redis replication to transfer it to other VMs, right? Okay, is it durable? Is it 100% durable? No, because you are doing periodic snapshots. There are chances of data loss, right? Then what we asked ourselves, like, okay, how much of data loss? Can we even time bound? Like, okay, what amount of data we are going to lose? And is it okay for our production business use case, right? And it turned out to be that we are okay losing small amount of time-bounded data, because what it will lead to is, okay, some of my reservations have gone, so I will start doing overbooking, right? But that was okay if it is bounded. So yes, that worked us very well, and we used this Go serialization, which is a Go specific serialization format, to convert the entire data into and transfer it into Redis. Yes, is there a better choice? Yes, protobuf is a better choice. It is more matured, it's more efficient, and it's language independent. But yeah, I mean, we chose to use Go, and we may switch to protobuf later on. And yes, in production, this is running, and we have found that Redis co-hosting works very well because, as you know, Redis is a single core. It uses only one core, and it's very resource frugal, and it makes very sense to use this in this way. It doesn't eat up the resources for AChem. It's minimal overhead, and you achieve the replication. Right? So, okay, now that we have transferred the data over there. Is that it? So the point is, we also need to find out, like, okay, who should accept the writes? Say from client perspective, where should they write to? And let's say that is not available, then whom should I write next? And from a server perspective, like, okay, who is the leader? Like, who should be the leader? Start accepting writes, and whenever the leader goes down, who should decide that who is going to be the next guy who should start serving the request, right? So it needs leader election. There are a lot of common frameworks available. Again, this can be implemented from scratch ourselves implementing a raft algorithm ourselves and stuff like that. But then again, there are frameworks available. Like most popular choices would be Zookeeper, etcd, Console, right, and many other. We chose etcd. Etcd is a distributed key value store which is consistent and highly available. It by itself internally it implements raft to arrive at consensus and make it consistent the data transfer. Updates. So we used etcd just because it was like its simplicity. It is very simple to deploy in production. Like it's a single binary and you start it up and that's it. Minimal configurations, and any beginner can just start using it like in very less time. And the APIs are also like pretty simple compared to Zookeeper, right? So we use etcd for the coordination framework. And we have written a generic lead election library, which we call Kingsmoot. So this is a common, this problem is very generic. It has nothing to do with logistics counters or something else. So we wrote a generic lead election library, which can also be used outside of ACAM. What it does is 3 things. Given a potential list of candidates, decide who is the leader, monitor the leader, and if the leader goes down, do a leader election again. And notifications, right? There are notifications available for clients also to discover that if there is any change in the leaders, like discovery. So these are the 3 basic things which it needs to do. And it is built based on the following low-level constructs provided by etcd. They are atomically put a key if absent, and the key will have an associated TTL also, and you refresh the TTL, and you also can watch on a key for changes, right? Okay, so these are the 3 building blocks to build a lead election library, which we have done. So how does it work is when the node starts up, like let's say ACAM server starts up, the Kingsmoot libraries are glued into ACAM, and in the startup sequence, the Kingsmoot library comes first, and he contacts the etcd server, and everyone tries to write a predefined key, and only one will succeed, and he will become the leader. And once he's elected as a leader, he's going to tell ACAM that, okay, now you are the leader, and internally it's ACAM's responsibility to load from Redis and start ready for serving requests. If you see here, so if he's the leader, he loads from, like, once Kingsmoot library has decided that the current node needs to be leader, he asks ACAMs to, like, okay, now you become the leader. And it's ACAM's responsibility to just load up the data from the co-hosted Redis and start ready to serve requests. And so whoever could not write the key, that means there is already a leader exists. So he gets the existing leader's data, and he gives that data again, like the Kingsmoot reads that data and gives it to ACAM and say that, okay, now you start as a follower. So what it needs to do is, like, okay, start in follower mode, don't accept any requests from clients, but configure your Redis to start replicating from your master Redis. So this gets auto-configured. So the complete setup is automatically done. If all you need to do would be to just fire up those 3 servers and you're done, right? And additionally, once they have, the followers will also put a watch on the key, so that whenever and the leaders will need to keep refreshing their key. So once, if I have become the leader, the key will be there only for the TTL time period, and after that key will disappear. So the leader will need to continue to refresh the keys, like before TTL expires. And this acts like a monitor, like heartbeat. And if master could not refresh within the TTL for any reasons, like the key vanishes and the followers gets the notifications and the elections gets triggered, and one of them will become the leader again. So it's pretty straightforward. And the client will also latch on to etcd to discover the current master, whom should I route my request through, and also client watches on that key, so that whenever any leader election changes happens, client will discover that, okay, now that there is a new master, let me route it to the new master. So, but again, is it 100% highly available? No, I mean, there would be short period of time where the requests will fail. But again, we were okay. The time period with where the request fails is so less that we were okay with that. Right? So, and again, the Kingsmood library is written in Go, and also it has Java bindings for client side, because the applications which we are talking to ACM was written in Java. So we had Java bindings as well as Go bindings. And yeah, so that's how we have tackled the hard replication problem in a much simpler way, right? The time to develop this was like pretty less, because ours was to just piggyback on the already available solution. Now coming to, okay, after since we have covered like what approach we have taken and how we have done like the ACM development, now coming to how it performed finally, right, in production. So these were our production numbers which we have validated, right, scaled and validated for. The number of capacities tracked are over like 1.5 million, and the peak QPS a single box could handle, single very mediocre box could handle was 150K QPS. And the latencies were like the median latencies were less than 2 ms, and the 99th percentile latencies were less than 25 ms. And availability was like 5 nines, and we haven't seen any failovers getting triggered in our production. So this summarizes is worth the effort. At least we have like in production, these were the numbers we saw. And just to summarize on like, okay, finally, like what are the big wins with ACM? Like, yes, what are like, is it worth the pain, right? Yes, faster time to market. As it may sound scary, okay, oh, write your own database, like as scary it is, but finally it turned out to be that we could get our first version up and running in like 1 man month and 2 calendar months, which is pretty less for a database. Easy maintenance, yes. The number of lines of code, anyways, it's like less than 2K lines of code overall, and like all team members started contributing to it without any issues, because it's like very smaller code base and easy to maintain. Higher performance, as Tahir had mentioned, without network the performance were like 10x, and the network is the only bottleneck right now. And complex query logic expressed in easy imperative language. Yes, your queries have become your program, right? Whatever query you need to be written in Go, and you can really unit test and vet that everything is fine. So it becomes much simpler in terms of defect analysis or debugging. The total control over schema evolution, as we talked about, in production, we have already changed the schema at least 2 times. We had to change the schema, and without any service downtime, we could do that because we had total control over the schema. We could like do it. Yes. Okay, so that's it. So I will call upon Tahir again to explain like, okay, what we see as future of ACM. Yes, this is just the beginning of the journey. You would have figured out that okay, where and all we could improve, but we had made a choice like, okay, some of them they are very important to me, and some of them, yes, I can wait and I can validate my idea in production and then start adding to it. So yes, he'll explain like where we see.
Tahir and Hari, this is your last minute. You
Sure.
do not have time for Q&A post this.
Sure.
2 minutes more, right?
No, sorry.
Okay.
You were late in pausing the timer. Okay.
You were late with your presentation, actually.
Okay. So the future, like once when we set out to build this database, we did not have any grand plans for it. We just wanted to solve a business use case as fast as we could, right? But seeing as it has performed well in production, what we want to do is take ACM and turn it into a DB development toolkit. So there are only a few hard problems in databases, and most of it is around durability and networking, etc. Right? So what we want to do is basically take ACM and allow you to plug in your code into that infrastructure which we have already provided, and also make some improvements like move away from snapshotting and use incremental replication instead of that, and improve on the network a little bit more. We have problems with small payloads, etc. And they're not terribly difficult problems to solve. It's just that they take a little more time. And then who knows? Maybe we might offer this as an open source solution. But until then, there is another option, which basically came up just the middle of this year and kind of validates our approach, as in trying to write custom databases to solve hard business problems, which is Redis modules. So it's essentially the same thing as what we want to do with ACAM. It uses Redis as a database development toolkit. You can write Redis modules, which are shared object libraries, to define your own data structures and specify queries on them, specify your custom commands on them. And they can leverage some of the existing Redis infrastructure already. And the advantage, of course, is that you're building on a mature platform. But on the other hand, there are some key differences. One is that Redis is single-threaded. So if you have queries that might run a little longer, as in our case, which we need to scan a lot of data, that may be a bottleneck. The other is that you don't get direct access to the memory layout. So you have to serialize your data structure into some string, and then you do that set as per query. And the command syntax offered by Redis is just plain text, right? So you'll need to build your own command syntax on top of it. So those are a few limitations, but if this works for you right now, I mean, you can already start experimenting with this. So the key question in the end of this talk is, do you need a custom data store? And I would say you can write your own data store if it helps you avoid pushing boundaries. Like in our case, we were running into limits around how many queries we had to perform or how much data we had to transfer, etc. And if you find that your data structures are such or your queries are such that it's better to just hardcode them in your own native logic, yeah, go ahead and write it. I mean, like, none of the team that worked on this is an expert in writing databases. We are not experts in networking either, and that's the whole point, right? I mean, even with some very somewhat reasonable knowledge of how to write data structures and how to write some networking code, we came up with something that actually ends up competing with mature databases. So you can do it, yeah. And this is the team that worked on it. Hari and me and all the contributors are, I suppose, here already, right?
Thank you, Tahir and Hari. I'm going to have to cut this short. Guys, you all can move on to the main Audi for decoding fashion context with using word embeddings. Those interested, and we'll have the next talk start here right away.